Okay, now this next section has to do with the reaction quotient. Q-U-O-T-I-E-N-T. Okay, the reaction quotient is usually represented with a capital Q. And the idea is that the equilibrium expression is only mathematically true once the reaction has actually reached equilibrium conditions. But so if I have 3H2 plus N2 in equilibrium with 2NH3, you should be very familiar with this reaction by now. If I take the concentration of NH3 and I square it, and I divide that by the concentration of hydrogen cubed and the concentration of nitrogen, is that going to equal K? Well, the reality is it won't necessarily equal K unless you've given the reaction sufficient time to reach equilibrium. This is only true if we have equilibrium concentrations, even though we don't write the EQ there every time. Well, what if I don't have equilibrium concentrations? Let's say I've just started the reaction and I can see that the concentrations are changing. The reaction has not yet settled down at equilibrium, but I still measure those concentrations and put them in this formula, and I get a number. Is that number useless because it's not at equilibrium? No, that number can be really useful, and we call that the reaction quotient. The reaction quotient is just this quantity under non-equilibrium conditions. And another way to say that is that K is actually a special case of the reaction quotient. K is just the reaction quotient under equilibrium conditions. And then under non-equilibrium conditions, Q can be whatever it is. Q can be large values, it can be small values. And the point is that by comparing Q to K, we can make a prediction about which direction the reaction is going to proceed in order to reach equilibrium. So let's consider if Q is greater than K. So for this reaction, if Q is greater than K, then that means that the concentration of ammonia is too high, the concentrations of hydrogen and nitrogen are too low. And so if Q is greater than K, we can predict that this reaction will shift toward the left in order to reach equilibrium. We'll need to consume some of that extra ammonia. We'll need to generate more hydrogen and nitrogen. If Q is less than K, then that means that the amount here in the numerator, the products, is too small. The amount in the denominator, the reactants, is too large. That's what makes Q be less than K. And so the reaction will have to shift toward the right, toward products, in order to achieve equilibrium. So by calculating Q and comparing it to K, you can make this determination of which direction the reaction is going to have to go in order to reach equilibrium. And of course, if Q is equal to K, then you are at equilibrium already.